Okay, so now let's talk about acceleration. Acceleration is a very, very important quantity, and so it's going to allow us to study motion in which the velocity is changing. What is acceleration? Well, acceleration basically measures the rate of change of velocity, how much your velocity is changing. If you are driving and then you push the pedal, and then you go from 40 miles an hour to 60 miles an hour, then you have accelerated. So there's acceleration here because your velocity is changing. Typically, we talk about the instantaneous velocity. So we have the instantaneous velocity, so we can talk about the change in velocity, right? And that'll be what? Well, by definition, would be final velocity minus initial velocity. And now the acceleration is going to be defined as, well, the change in velocity divided by the time that it took for that change to happen. So, and that is Vf minus Vi over delta t. So that is the definition of acceleration. And we're going to see a few properties of this new quantity that is going to be very useful. So the units of acceleration, well, I mean, so you have units of velocity. Units of velocity are, say, in international units, meters per second. So then the units of acceleration is delta V over delta T. So you have meters per second divided by seconds. So then that's going to give you meters per second squared. So basically it is meters per second every second. So for instance, let's say you have a car that is moving at 60 miles per hour, which is equivalent to 27 meters per second. It goes up to 27 meters per second in 3.6 seconds. What is the acceleration? Well, let's just think about that. So the initial velocity is 0 meters per second, right? Because it starts from rest. The final velocity is 27 meters per second, right? So that's the final velocity. The acceleration is final minus initial, which is 27 minus 0, divided that by the time that it took for that to happen, which in this case is 3.6 seconds, right? So these are meters per second. So then you get that the acceleration here is 7.5 meters per second every second. So every second the car is going 7.5 meters per second faster. So how do we represent the acceleration? So the easiest way to think about it is to look at the velocity versus time graph. So here we have two velocity versus time graph. Remember the rise and the run and the position versus time graph are going to use the same, but the rise here is going to be the change in velocity and the run is just the change in time. So we have change in velocity divided by change in time, that is the slope. That measures how steep this graph is, and that tells you what the acceleration is. So what this is this quantity here divided by this quantity here tells you what the acceleration is. So let's look at a more complicated graph, if you will. So we have velocity versus time here. So in this case, the velocity is changing from 0 to this value here, right? Then the velocity goes from here to here and it doesn't change. And then it goes from here to here and back to 0, right? So here we have a positive acceleration, right? So during this stage, the car speeds up. During this stage, what is the acceleration? Well, the velocity doesn't change. So the acceleration is 0. And then in going from here to here, what happens? So the velocity goes from some value to 0. So that's a negative velocity. The acceleration is decreased, the velocity is decreasing. is a negative acceleration. So let's look at the sign of the acceleration in a little more detail. So if you have a velocity versus time graph with a positive slope, which looks like that, then the acceleration is positive. It doesn't matter whether the velocity is negative or positive, right? If the velocity is increasing, meaning this graph has this type of slope, then the acceleration is positive. In the other case, if the slope is negative, right? If it decreases like that, it doesn't matter whether the velocity is positive or negative, right? So you're going to have a negative acceleration. So let's look at a simple example here, right? So we have a rocket. So the rocket is fired, and then it goes at, there is a change in velocity. This is the time. So it goes to 27 meters per second in 1.5 seconds, right? What is the acceleration? The acceleration is 18 meters per second squared, which is 27 divided by 1.5. What that means is every second, this rocket here is accelerating the velocity is increasing by 18 meters per second. In the first seconds, the final velocity is 18 meters per second. In the second, the final velocity is going to be 36 meters per second, and so on. So another way to calculate that number is to take the rise, which is 27, right? And then divide that by the run, which is 1.5. So constant acceleration equations. So these are the equations that you're going to use the most in this chapter. So the acceleration by definition is change in velocity divided by change in time. So change in velocity is final velocity minus initial velocity divided by delta t, or final velocity. You can rearrange this equation algebraically. I did that in the previous slide. And then you get that the final velocity is equal to the initial velocity plus a delta t. This is one of the first equations that we're going to use. It's only true if this guy is constant all the time. So let's look at constant acceleration equations. So let's see, we have the velocity here, right? And then, so this is your time interval, right? So this is your rise. So what is this? This is delta v, right, by definition. But it is also ax delta t. So you get that delta v is equal to ax delta t. And so, and let me just erase here. And so then delta v is ax delta t, and delta v is vf final minus initial, which is ax delta t, or final is equal to initial plus ax delta t. So this here is an important equation. I'm not going to derive this in the slide today. If you need me to, I can make another video where I'll go through this quick derivation. But all it's saying is that if you know the acceleration and the initial velocity, then you can find the position, the final position, using this equation here. So this is called the position equation for a motion with constant acceleration. And finally, the other equation that we have is this one here that says the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times delta x. So I don't want you to memorize these equations, although after you use them a lot, you'll see that they'll come natural to you. The derivation for this equation is in the book. So go and read that. So we have three equations that are very important. So we have final velocity equals to initial velocity plus acceleration times delta t. This allows you to get the velocity if you know the acceleration and the time. Then you have final position equals to initial position plus initial velocity times delta t plus 1/2 times the acceleration times delta t squared. This is a quadratic equation, and this allows you to get the position versus time given the acceleration and time. And finally, you have this equation that says the final velocity squared, and there is a square here and here. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position. So these are the main equations that you're going to be using, and in the examples that are in D2L, you can see some examples of where these equations are used. So let's finally look at a problem here. So how do we go about solving problems with constant accelerations? Well, there are two things that you need to do. Just read the problem properly and then think of a strategy to solve the problem. As you read the problem, you do a few problems, you'll get familiar with the different strategies that there are to treat these problems. So it is important to draw a picture, a visual overview of the problem. I'm going to stress this a lot during this class. Please draw a picture because it's going to give you a very good representation of what you need to do. Then after you have your strategy and you solve the problem, you try to solve. That means, well, you start looking for equations that might help you. You start breaking your problem into pieces to work. And then finally, after you get a solution, you assess the solution. So let's look at an example here and see how that strategy would work. So we want to calculate the minimum length of a runway. So we have a Boeing 747, and then the acceleration is 2.7 meters per second squared. The Boeing needs to reach a minimum speed of 70 meters per second to be able to take off. What is the minimum length that a runway should have so that the Boeing can actually do what it needs to do? So let's look through the steps. So first we strategize. So you are given the acceleration. You're also given this here. What would this be? This is the final velocity, right? So you're given the acceleration and the final velocity. And what do you need to find? You need to find the minimum length. What would this be? This is a delta x, which is x final minus x initial. So that's now you have an idea of what you know and what you need to find. That's what part of what you do in the strategy. So now you would draw a picture. Here you have a pretty good picture, right? So you have initial and final. And then you have things that you know or you want to know. So you have the initial position, initial velocity, initial time, final position, final velocity, and final time. And then you have the acceleration here, right? You can also draw a motion diagram that might help. And then it is good to have a table with what you know and then what you need to find. All right, so now that we know this, we can start looking at the equation. So a really good equation that would help here is final velocity equals to initial velocity plus acceleration times delta t. So you know that the velocity that you need to reach is 70 meters per second. The initial velocity, you're going to start from rest. This is the acceleration, and this is delta t. So here, now, you have the time that it would take for the plane to reach 70 meters per second. Okay, so now what do we do with that? Then we need to find the distance. So to do that, We use this equation here. Final position equals to initial plus initial velocity times delta t plus 1/2 the acceleration times delta t squared. Initial position is 0. Initial velocity is 0. So all these are 0, and all you're left with is this, which is 1/2 times the acceleration and the time squared that you found before, and that gives you a run weight of 940 meters, or roughly 1 kilometer. So that's the minimum run length that you need for the plane to take off. So does this make sense? This part is very important. It says that your answer is good. If you have gotten 1 meter, then you know something is very wrong. And if you have gotten something like 100 miles or 160 kilometers, well, that's also wrong. That will be the size of a huge city. But 1 kilometers, which is roughly 0.6 miles, sounds reasonable. So you say, well, my answer makes sense. So that is what you do when you assess these problems. Okay, so this finishes this video. I hope you have time to look at the other examples, and let me know if you have any questions.